Thank you. The chair recognizes the gentleman from Florida, Mr. Posey.
Thank you, Mr. Chairman. Thank you for calling this very interesting hearing, and thank the witnesses for their informative testimony. Do you believe, this for anyone on the panel, for all on the panel, there's a risk that in starting to build geoengineering capabilities, we could lose control of them, and how do you think it would compare to the risk of bioengineering and nanotechnologies?
I'm willing to take a stab at it. I think scientists are all concerned about the possibility of this, us losing control of it and adopting it. But I personally feel that it works better to operate from a position of knowledge about it rather than the absence of that knowledge. And I think the cat's kind of out of the bag at this point in the game that the technology is possible. So I would prefer to be spun up on what it's...
Okay. Ms. Wanser, you had your hand up next.
Well, solar climate engineering technologies actually have a high barrier to entry. So they're relatively expensive to engineer and relatively expensive to measure. And they scale linearly. So you evolve solar climate engineering technologies with the number of dispersals you have. They're very easy to see and detect. Whereas nanotechnology and bioengineering techniques have very low barriers to entry. You can now buy a kit to engineer organisms with CRISPR for less than $200, and you could release them into the wild. So the challenge with things like bioengineering is that they are low barrier to entry and self-replicating. So in some senses, solar climate engineering actually is less challenging from a governance perspective, provided we have a framework in place. I disagree a little bit with Dr. Majkut that we already have one. I think it's part of what we would want to define in conjunction with the research program. But I think some of the challenges here are a bit more straightforward than they are in some of these other fields.
Okay. Anyone else care to comment?
Yeah, I just wanted to add, if we did put aerosols into the stratosphere at any point, the lifetime in the stratosphere is about a year or two. And so whatever we put up there is just going to come back down. That also means that if you want to maintain it, you have to constantly be putting more in. So there's less risk of it running away when you're actually deploying it than there would be for, say, a biotechnology type intervention.
Okay. Any hard evidence on the effect that subsurface activity has on the atmosphere? I mean, we know what ended the last ice age. It was an asteroid strike, which basically created a Gulf of Mexico and darkened out the Earth for many, many years, allowed it to freeze over. There are some conditions that exist here now that have the potential to recreate that catastrophe within. Some of the research I've seen at Yellowstone, big volcano in the Azores that they say will cause a 100-foot-high tsunami, but your thoughts on how that may affect us?
Well, relevant to these questions, there's a volcano, Mount Agung, which is on currently a level 3 eruption watch. So we may have a natural experiment coming up should it erupt and inject sulfates into the atmosphere. Then we would see a repeat of what previous volcanoes have done and probably some cooling influence. And thankfully, the scientific community, I believe, is ready and standing by to observe that and understand the processes as best they can. That's certainly true.
If I might follow up,
Rasch?
it's to say just that the scientific community is very interested in a rapid response team for watching over these volcanic eruptions, but they are sort of assembling it as we speak, and it's not maybe quite as far along as Joe mentioned.
One last question. What have other countries done so far in this realm?
The rapid response team is an international effort. There's certainly a very large and interested part of American U.S. society, scientists participating, but that is an international activity.
Okay. Thank you, Mr. Chairman. Time has expired.
Thank